Welcome back to lecture 14. In the last part of this lecture we derived the cross model, and we saw that the cross model could be used as a descriptor of rheological change due to interaction re-establishment and interaction breakup in a structured material. We saw that the cross model predicted a flow curve that had a low shear rate and a high shear rate Newtonian plateau. What we're going to do this lecture is use the cross model to examine a very important material property, that of thixotropy, and this is a time-dependent behaviour. So we're going to look at structure breakdown and structure reformation once again, and we're going to look at the time-dependent manner in which this can affect the viscosity of a material. We're also going to look at data from real materials, and we're going to see what experiments we can do to highlight whether or not a material exhibits thixotropy as part of its response. So to start with, let's formally introduce what we mean by thixotropy. When we talked about generalised Newtonian fluids, we said that the apparent viscosity is instantaneously linked to the deformation rate, the shear rate. If we had a change in deformation rate, the apparent viscosity would instantaneously change with that deformation rate. So for example, if we have a shear thinning material, perhaps described by a Corot-Yasuda model, as we increase the shear rate, we will see an immediate response in the viscosity. If we instantaneously decrease the shear rate, we will instantaneously see an increase in viscosity. So the important word here is instantaneous. There are no kinetics within these generalised Newtonian descriptions. Now let's contrast this with a thixotropic material. In a thixotropic material, if I look at the response between apparent viscosity and shear rate, what I see is that it takes time to respond to a shear rate change. So for example, I might have what may at first sight look like a shear thinning material. I might increase my shear rate from gamma dot 1 to gamma dot 2, and I will see my viscosity gently drop over a period of time. It will not be an instantaneous response. Likewise, I might stop shearing my material, and then it might take a measurably long time for the viscosity to increase back to its starting value again. So thixotropy involves time as well as deformation rate. So we're going to illustrate this now with the cross model. We're going to look at the step deformation response of the cross model, and I've put the response there on the board for you, plotted as gamma dot as a function of t. Let's assume that over infinite time my shear rate gamma dot has been gamma dot 1, and that my material is in a steady state response. So the viscosity has changed and it's not going to change anymore with gamma dot. Let's say what I do is I increase gamma dot 1 to gamma dot 2 and then observe my material after that change. So gamma dot 2 will be constant, and what I want to see is how my apparent viscosity behaves. So here on the board is the differential equation that corresponds to the cross model. The terms highlighted in blue are those terms required to reform a structure. Those terms highlighted in orange are those terms that govern the breakup of a structure. Now, what I want to do is to find n, hence eta, as a function of t. So I'm going to group together all terms that are constant to start with. I've said that gamma dot is constant because I'm only observing n after I've made that step change. KdR here is my material timescale, it's that equilibrium constant if you like. N is what I'm interested in, n naught is the initial number of interactions, so that too is a constant. So, with a little bit of rearrangement, and let's group together a whole bunch of constant terms in the parameter a, I can see that 1 over kr, my reformation timescale, dn by dt on the left hand side, is going to be equal to n naught minus an. And if we squint and look at that, we can see, this is a logarithmic type integral. Let's make this nice and easy. Let's substitute the right hand side, and let's say that u equals n naught minus an. And on the left hand side, minus 1 over a kr is simply du by dt. So the integral we end up with is this, written here on the board. It's 1 over u du equals minus a kr dt. let's look at the integration limits. When time equals 0, let's say I have u1, and what I want to do is find arbitrary u, which corresponds to arbitrary n and arbitrary eta, at arbitrary time t, sometime after we've made that step change in deformation rate. So there's that integral. Let's go ahead and integrate, and we can say that u equals u1 e to the minus a krt, and we can see within that exponential decay now we have our reformation timescale response there. So if we substitute n back in and then remember our expression for apparent viscosity, we can write an expression now that allows us to work out what the apparent viscosity response is, according to the cross model, to a step change in deformation rate. And there it is written on the bottom of the board as a combination of these two exponential terms. Let's see what this predicts. So now on the board, I've written a reminder of the deformation rate change. We have that step increase in deformation rate from gamma dot 1 to gamma dot 2. Now on the board I'm plotting the viscosity response. Now note, the x-axis is time, not shear rate. My shear rate is constant, don't forget. The x-axis is time. The y-axis is apparent viscosity in arbitrary units. And what we can clearly see here is that the apparent viscosity takes time to adapt to the new shear rate. Let's extend this logic. A cartoon there on the board now depicts a step decrease in deformation rate. So I've gone from gamma dot 1 to gamma dot 2 now, which is lower. Hopefully, as one might expect, if we plot apparent viscosity as a function of time again, what we see is the increase in apparent viscosity that corresponds to that decrease in deformation rate again takes time. So this really underlines the important behaviour of thixotropic materials. The viscosity of a thixotropic material not only depends on the deformation rate, it depends on the amount of time the material has had to respond to that deformation rate. And remember, that response is all about a competition of breaking attractive forces and re-establishing attractive forces. What about real materials? What do we see experimentally? Well, I'm going to give you some examples now of a well-known sandwich spread, and I'm going to plot the data as apparent viscosity as a function of shear rate for steady shear experiments in a rotational rheometer. So parallel plate setup, fixed top plate, rotational bottom plate. I might have used roughened plates to eliminate the presence of slip. And the first experiment I'm going to do is to very carefully increase the shear rate from a low value to a high value and watch my apparent viscosity response. So there we have my apparent viscosity data as I ramp up shear rate, increase shear rate from a low value to a high value. I have capped the maximum gamma dot such that I keep my material between my parallel plates. Don't forget the discussion we had about material ejection in parallel plate systems. We don't want to lose the material because we're going to do another experiment on it. What we're going to do now is measure apparent viscosity as a function of shear rate for decreasing shear rate immediately after I've achieved the highest shear rate I'm going to allow in the system. So I sweep up in shear rate and then sweep down in shear rate. And look, I get a different viscosity response. We can see two things about this. Firstly, the blue data points are not the same as the orange data points. They're nearly a decade in viscosity different, nearly a decade in viscosity different. The second thing that we see is that there is enough time to start re-establishing attractions within this material. So we do register an increase in apparent viscosity. Now, if one immediately after that downward sweep depicted by blue increased viscosity again, we may expect the apparent viscosity to follow that blue curve. If we were to rest the material and then increase in shear rate again, we'd expect it to follow the orange curve. So if we're thinking about this in a processing context, we have to be very careful what viscosity measurements we use to design a system if we've got a thixotropic material. Because if your material structure is destroyed by the first high shear process that it meets, then it's always going to be following the blue curve in this diagram. If there's sufficient rest time, then the material response will start to follow the orange curve again. And with over a decade difference in apparent viscosity, that has quite a severe consequence for how you design the material for the pressure drop in the system. The pressure drops are going to be very, very different depending on the material response. Let's look at a different well-known sandwich spread. So again, I'm going to do the same experiment. I'm going to use a parallel plate rheometer. I'm going to sweep up in shear rate and then sweep down in shear rate. The sweep up in shear rate shows that again I have a decrease in apparent viscosity with increasing shear rate. My sweep down in shear rate looks quasi-Newtonian. There's no discernible difference in apparent viscosity as a function of shear rate. So what this is saying is that the material reformation timescale is far, far, far longer than the timescale associated with this experiment. Again, if I was to increase the shear rate immediately following that decrease represented by the blue data, I would probably get my Newtonian behaviour back. And so think about this for a piece of processing equipment. It may be possible that a shear thinning material, or a material that presents a shear thinning, might be behaving in a Newtonian manner because of this thixotropy. So let's see how we might now probe the reformation timescale of a material such as this, because the experiment that we've depicted here doesn't have a sufficiently long enough timescale to allow us to observe the re-establishment of that higher viscosity. So what I might do is, over a course of a long time, gently take measurements. So this graph is apparent viscosity as a function of time, and the protocol that I'm going to adopt is, before time equals 0, I've got my high shear rate. So my material is completely sheared and the lowest viscosity in the system has been established. What I'm then going to do over a period of maybe 6 to 8 hours is have small periods where I gently shear the material, measure its viscosity, and then stop, because I don't want to break the material down by virtue of the measurement that I'm trying to make. What one might see, again this is real data from a well-known sandwich spread, is the timescale for reformation may be of order hours. And this is a sort of experiment that we can do to determine that. And again, these kind of data have great ramification for how we might design a process that manufactures a material such as this. So let's recap a few key points. We've been discussing thixotropic materials, and the key thing about thixotropic materials is that there is a time for them to respond to deformation rate. We looked at the cross model in terms of thixotropy and saw that we can use it to predict a reformation and destruction of attractions, hence an increase or decrease in kinetic for viscosity change as a function of time. Experimentally, we've seen that thixotropy can be revealed by doing shear rate sweeps. We sweep up in shear rate and back down in shear rate. Do we see the same data? Then we probably sweep up in shear rate again and back down again and see what data we get. And what we will probably see is the first increasing shear rate sweep will have higher viscosity values than the subsequent sweeps in shear rate both up and down. We've also seen that for materials with very long recovery timescales, we can use intermittent shear experiments to probe recovery time and therefore enable us to quantify that timescale.